In this section, we're going to talk about radian measures. So, you've dealt with degrees, minutes and seconds, and whatnot. But in this chapter, we're going to introduce this idea of not really working with degrees at all, but working with radian measures. Now, just so that you kind of have like a little bit of motivation, well, for the most part, you're going to be dealing with these functions, like for instance, like f of x equals to cosine of x, or maybe you'll deal with this function like g of x equals to sine of x. Now, the main thing that you have to realize is that whenever we deal with functions of this nature, we'd like to think that x is a real number. So, rather than saying, well, x is a degree, which I mean, mathematically, we're taught to normally deal with real numbers and whatnot, as long as there's no restrictions. So, it necessarily, or I guess in a way, it would make sense that we wouldn't necessarily work in degrees because maybe, yeah, maybe it'd be better if we can just work with something else that makes more sense that you can input into a function. Now, where we kind of start is by looking at, for instance, we can look at a circle, perhaps like with radius r. So let's say that we have a circle with radius r, and okay, so this is r, this is negative r, and that's r, and this is negative r. Now, in this case, say for example that we were to draw a ray. So we draw a ray, and let's say that, for example, that we label a few things, like for instance, the angle that forms. So like we'll just say theta. But the other part of this, aside to knowing that the radius is r, is that the length of the curve right here is also r. So we have r, and then we have r right there. Now, that's actually how we end up getting a radian measure. So, for instance, we know that we know, for example, that the circumference of a circle is 2 pi r. Now, that's more or less the same idea, is that basically you have that if you want to measure the arc, it's usually just r times theta. Now, since I said that s was equal, or r is equal to the arc length, well, in that case, this would give us the following: r equals r times theta. But what does this do to us? It gives us this theta equals to 1. But in this case, you have to be a bit more specific, like where we say that this is going to be what we call 1 radian measure. Okay, now this is a little strange because now it's like, okay, well, I have this thing called 1 radian, but I'm not even sure what a radian actually is. Now, the radian measure um, can be thought of as a degree measure in that case, but where we're just going to say that it's really dependent on the units that we're working with and also what is the radius in question. Like this could be radius 4. So in that case, you'd have that 1 radian measure would be equal to, um, well, it would have to be equal to its radius, whatever what units it is. But let's just think about it like this. If we go ahead and we redraw another diagram, and let's say that we draw our ray like this, okay? Now, here, this is roughly about a radian measure. So, like we have that, if we were to go like this, and then we go like that, this right here is my angle theta, but then this right here could be my 1 radian. Okay, so this kind of gives you an idea of like what a radian measure is going to be approximately, which it's a little more than 45 degrees in actuality. Now, take note that when I wrote down how I got my radian measure, I mentioned that it's found by using S is equal to R, and not R divided, but R times theta. Now, if I rearrange this and I say I have S divided by R, and this is theta, but let's say that, for instance, that S is equal to R inches. Okay, so in that case, you have theta is equal to R inches divided by, well, technically that means that R would have to be also in inches as well. But notice that this completely cancels out the inches and the radius to give us the equation theta equals to 1 radian. Okay, well, in this case, this is more or less me saying that a radian measure has no measure of units in this case. Okay, but again, there's going to be like some conversions and whatnot and being involved in, like if we're dealing with feet, meters, kilometers, etc., like what would be the conversion? In either case, usually sometimes the dimensional analysis tends to get lost, but it'll work itself out. Now, because I'm talking about units and whatnot and conversions, well, let's think about this. How exactly can we convert the degrees to, let's say, for example, radians? Well, think about it like this. If I was to rotate, 360 degrees, well, I know that, one rotation is equal to 360 degrees. But remember how I was saying that, we can say that, we're looking at the arc length or the measure of the curve. Now, in that case, that tells us that one rotation is equal to 2 pi. Okay, but let's go ahead and be a little more precise on this. So from this, we're saying that basically 360 degrees has to equal to 2 pi radians. So there's our equality. Our equality states that 2 pi radians is 360 degrees. Now, what that basically means, furthermore, is that 180 degrees is equal to pi radians. So in this case, we have a nice little equivalence for, like what is, for example, like what is a straight angle? Well, it's just half of the measurement, so that's going to be that, pi radians is equal to 180 degrees. Now, what we can then say is that, furthermore, we have that, well, notice this. We have that basically 1 degree is equal to pi over 180 radians. Now, I'm going to go ahead and just say RAD for radians. It's fine. Or we can actually say that 1 radian is equal to 180 over pi. Now, in this case, note that, we're not going to include the radians for pi, or, well, it kind of works itself out that the dimensions match or whatever. But if we ever drop the units, it's as long as we kind of have that understanding that it kind of works itself out when you're doing the conversion. Now, if we want to come up with a method So the key is kind of practicing this method. So the method is that you're going to take your degree measure that we can call A, and you're going to multiply it by pi over 180. Okay, so this is basically how we can say that we're going to go from uh, right, so this will be degrees to radians. So we multiply by pi over 180. Now the other is that if we take A, or let's say like this, B, if we take B and we multiply it by 180 over pi, this is a method of going from radians to degrees. Okay, so in either case, we have kind of like a nice little shortcut in a way that we can just multiply that. So let's go ahead and say, for example, that we want to go from degrees to radians. Now, in this case, like let's go ahead and just look at 108 degrees, and then we'll look at negative 115 degrees. Now, the method basically dictates that, for part A, you would take 108 degrees and multiply by pi over 180. Now, I will say that, for example, just because we don't have the radians degrees, you can see that the degrees will actually cancel out. So, it goes back with saying that it kind of works itself out in this case. Now, when you go ahead and you multiply through, so basically you have that the degrees is going to cancel out, and you're going to end up with 108 pi divided by 180. Now, there's more to that though, for instance, because you have that 108 and 180 do have a common factor, which in this case is 36. So we can reduce this even further by doing, yeah, 36 times 3 divided by 36 times 5 times pi. So basically we'll see that that equals to 3/5 pi. So that's actually the answer is 3/5 pi. Okay, now keep in mind that that's the exact value, but it's not the approximation. Now, let's say that, in part B, you basically want to do the same thing. You have negative 115 degrees multiplied by pi over 180, and that's equal to negative 115 pi, and that's divided by 180. Now, in this case, like if you want to try to reduce this as best as possible, um, yeah, we have to go ahead and look at what the greatest common factor is. So it looks like in this one it's relatively the same almost, but we're just going to go ahead and rewrite this as negative, let's see, negative 5 times 23 divided by 36 times 5. So this was all times pi, right? So you're just going to take the 5's and cancel them out. And basically this is going to equal to negative 23 over 36 pi. And then that's it. Now, of course, like, you can actually try this on your own, which you should. So go ahead and try to convert 330 degrees to radians. and see what you get, you'll kind of notice that, uh, you know, one of these will come back up again in terms of like, how do you find it? Um, Notice that as you are going to convert, notice that you can always use that 180 is pi, for example, if you're going the other way around though. So, and we'll see that like right now, like with this next examples. So in these examples, we're going to go from radians to degrees. Okay, so let's say that we go ahead and we look at the following measurements. So 11 pi over 12, and then in part B, we'll say we have 7 pi over 6. Now, these actually aren't too bad as it relates to, finding their solutions. So like 11 pi over 12, I know that I'm going to basically multiply that by 180 degrees divided by pi. Now, this is where, you would obviously reduce as best as possible. So we know that the pi's cancels out, but then notice that you have the 12 into 180, which in this case, 180 divided by 12 is 15, and then multiply that times 11, and you should get 165. So this gives us, let's see, yeah, we'll just write it like this. So we have that, okay, so again, just to kind of recap, we have that the 12 did cancel out into 15, and that's why it's going to equal to 165 degrees. Okay. Now, with 7 pi over 6, that one's actually a little easier because you have 7 pi over 6 multiplied by 180 over pi. Now, keep in mind that basically that the pi's do cancel out. Okay, that much is clear. But then you have that the 6 into 180 is 30 degrees, which means that when you multiply through, that's going to give you 210 degrees. Okay, so you kind of will notice that some of these will come back up a little bit later. Now, in this case, like, you can kind of see that there's not really much to it as it relates to going from, degrees to radians or radians to degrees. You should definitely try the following, like 3.25 radians, and try to see if like you can convert that to degrees. Now, one thing that I will point out is that whenever the measurements is not included, like if you just see 3.25, that means that it's understood that it's in radians. So, which is kind of weird because, like, if you have sine of 1, that basically means that it's automatically understood that it's radians as opposed to degrees. Now, one thing that you do have to consider is that, you have to find your own way in terms of like, how do you do your conversion? Like if I had 7 pi 12ths and I wanted to convert that into degrees, remember I was saying that you can always just say 7 pi times 180 because 180 is pi and that's divided by 12. So in that case, 12 into 180 is 15. So in that case, you have 7 times 15 degrees, which is equal to 105 degrees. So, you can kind of use that to your benefit in terms of like, knowing that 180 is pi if you want to do the conversions. Okay, now before we move on, we need to look at this whole idea of radians versus degrees. So for instance, let's say that you type in sine of 30. Well, if you type in sine of 30, right now my mode is in degrees. But what if I change that to radians and I type sine of 30? So the difference is that this was degrees and it gave me 1/2. Sine of 30 degrees is negative 988, negative 0.988. So there's a big difference between, typing in the degrees versus the radians. In this case, the most common expression is sine of 30 degrees, which is a half. But, sine of 30 radians, you know, if you were to convert that, you would multiply that by 180, and then you divide the pi out if you want to know, like, what is 30 radians? Well, 30 radians apparently is 1,718 0.87 degrees. So that's way different than, sine of 30 degrees, which is kind of weird because it's saying that it's almost like -1, which means that it's probably coterminal to 270 perhaps. Like, you subtract 360, subtract 360, subtract 360 again, and one more time. So 278. So yeah, that is definitely close to 270, um, which explains why is it so close to -1. Okay. In either case, this is just so that you kind of get a clue on terms of, like, what's the difference between, doing sine of or cosine of 60. So that's -9.5 or -9.5. But if you change the mode, which is to degrees, cosine of 60 is actually a lot easier than it looks. So, like, if I do cosine of 60, but I know that it's in degrees, I get 1/2. So my point being is that for this, you just have to know kind of like what's the difference between the two. Now, this next part, we're actually going to look at what we call the unit circle. So let's say that we look at the unit circle, and that's a circle with radius 1. Okay, now in either case, one thing that you're going to realize is that there's these special angles within the first quadrant. Those being the 30 degrees, 45 degrees, and then you have the 60 degrees. Now, the best thing that you will need to do is to figure out, like, how exactly do I convert 30 to pi over 6, 45 to pi over 4, and then 60 to pi over 3. Now, you know, one way that you can do that, is, run through the conversions. Like, you have 30 degrees times um, pi over 180, and then you see that basically 30 into 180 is 6, so that's going to be pi over 6. But then you do the same thing with 45. You do 45 degrees times pi over 180, uh, but 45 degrees into 180 is 4. So you have that that's pi over 4. Similarly, if you look at, for example, pi over, or no, no, pi 6, not pi 6, 60 degrees. So 60 times pi over 180. Well, 60 into 180 is 3, so that's really just pi over 3. Now, from there, what the textbook really suggests is that, you draw these measurements like 120, 135, 150, 180, and so on, and you kind of just look at it like this. You can either look at it as multiples of pi, or you can actually look at it as multiples of these reference angles. So in this case, you have 120. Well, you think about it like this: 60 into 120 is 2, so 2 pi over 3. 135 divided by 45, 3 pi over 4, and so on. And you repeat that process until you reach all of them. Okay, so in that case, this is the reference angle of 30, 45, and then 60. And then you have again 60, 45, 30, and so on. So you can probably try to memorize this entire circle, or you can probably just go through the process of conversions of saying 120 is 2 pi over 3 and so on. Now, if you kind of think about how this is 180 and this is halfway between here, that kind of makes sense that, well, halfway between 0 and pi is pi over 2. And then similarly, halfway between pi and 2 pi is 3 pi over 2. So that kind of sets you up for those important quadrantal angles. Okay. Now you can probably pause the video and take a look at the circle and then see like what method that you prefer in terms of like memorizing or just learning the entire circle. Usually in class, I tend to just line them up and then just have you tell me, 120 converts 2 pi over 3 and so on. But if you want, block these out or whatever you have to do to kind of just get those measurements, locked down in either case. Now, eventually your goal is going to be evaluating trigonometric functions. So that's kind of what we'll do in this next part of the video. We'll try to find and evaluate uh, the trig expression. Okay, so the part that you're going to look at is cosine of 5 pi over 6, and then we'll go ahead and look at tangent of 5 pi over 3. Now, there are several different methods that you can do to determine, these trigonometric function values. So, one way that we're going to do this is we're going to look at cosine of 5 pi over 6. Now, 5 pi over 6 you can actually convert to degrees. So for instance, we have 5 pi over 6 multiplied by 180 over pi. Now look at this. 6 into 180 is 30, which means that this is really going to give us cosine of 150. So this gives us cosine of 150 degrees. Now this is just a matter of figuring out like where is cosine of 150 degrees. So cosine of 150 degrees, it terminates in the second quadrant, which means that basically this is our angle. Whether you want to call it 5 pi over 6 or 150, you're more than welcome to. But then furthermore, I know that this is 180. So in this case, this is going to be equal to cosine of, so you take 180 minus 150, so that's going to be 30 degrees. But because it's in the second quadrant, so you have all students take calculus, that means that it's actually going to be negative. Okay, now you still haven't figured out, like, what is cosine of 30 degrees? Well, try to recall back to, the 30-60 triangle. So we have 1, 2, and root 3. And this is going to be 30 degrees, and this is 60. So accordingly, it's going to be adjacent over hypotenuse, which in this case is just going to be negative root 3 over 2. And then that's it. Now, we could have also just used 5 pi over 6 and then just say pi minus 5 pi over 6, which gives you pi over 6, because it's definitely probably advisable that you work with that's pi over 3 and that's pi over 6. And of course, this is 90 degrees. So, it's more or less like preference in this case, like whether you want to do it that way or not. Now, let's say that we have tangent of 5 pi over 3. Okay, well, I already basically know that pi over 3 is essentially 60 degrees. So that's really just going to be tangent of 300 degrees. Now, tangent of 300 degrees terminates in the fourth quadrant. So I know automatically that, tangent of 300 degrees, it looks something like something like this. And, it's not really to scale necessarily, but, that's going to be what we'll say is that that's 300 degrees. Now, what that tells me is that the reference angle is basically 60 degrees. So I have tangent of 60 degrees. But you remember that I mentioned that all students take calculus? That means that it's actually going to be negative. So now I have negative tangent of 60, which if we look at our diagram over here, we have opposite over hypotenuse, or opposite over adjacent is root 3 over 1. So that's going to be negative root 3 divided by 1, which is negative root 3. And then that's it. Now, most definitely you should try more on your own. So I'll just say that you should try cosecant of negative 3 pi over 4. Okay, so try to look at that and see like what you get. Keep in mind that you are trying to find reference angles and coterminal angles still, but it's probably advisable that you work in radians for that matter. So that's actually what my next comments are going to be. So like for example, if you have that your angle measure is actually greater than 2 pi. So what if theta is greater than 2 pi? So for instance, let's say that you have 21 pi over 4. Well, one way that we can do this is, for example, if I have that I divide 4 into 21 pi, well, I know that it's going to be 5 pi plus, let's see, remainder pi over 4. But this doesn't really help me because the 5 doesn't really make sense. So in this case, I peel away a single pi so that it's in terms of, an even number. So I have 4 pi plus pi over 4, which means that I have 2 times 2 pi plus 5 pi over 4. So what that means is that the coterminal angle for this is 5 pi over 4. But then, the reference angle is pi over 4. Now, if you want to look at, what does 21 pi over 4 look like? Well, basically, you have that the angle measure, it rotated around the circle, like basically 2 times. So we have 1, and then we have 2. Okay, so 2, and then 5 pi over 4. So basically I need to do, let's see, 5 pi over 4 is going to terminate over here. Okay, so yeah, this is exactly what 5 pi 4 will look like. So in this case, you have that it terminates in the third quadrant, which basically means that the only one that's positive is tangent. Why? Because remember that all students take calculus. So if I want to find tangent, I know it's going to be positive versus sine, it's going to be negative, and so on. So that's my example of like, kind of knowing um, working with angle measures in radians and then converting it and working out the coterminal reference angle and also looking at the location to determine the sines. So in that sense, like you're gonna have to come up with your own method, like how do you evaluate those? But it's more or less the same thing. So like for example, what if you had negative pi over 6? Well, because it's less than 0, that means that you're just going to add 2 pi to it. So if you add 2 pi to it, you get 11 pi over 6, which basically means that the coterminal angle is 11 pi over 6. Now, what does that mean? That basically means that the angle measure, it actually did not really a full rotation almost, but let me see, 330, 330. So, okay, so that means that it kind of looks like that. So this would be 11 pi over 6. And then this right here is the reference angle, which is pi over 6. So it terminated in the fourth quadrant, which basically means it's going to be positive for only secant and cosine, or cosine and secant. I said it backwards, but I don't know why. So yeah, when you're working with these radian measures, you just want to make sure that you have kind of like your own method down in terms of like how do you reduce it and whatnot. Now, what I want you to do is to try the following. Try sine of 43 pi over 6 and see what you get for this trigonometric function value. Because essentially you're going to have to know how to evaluate these, especially if you want an exact value. Because, like, for instance, I know that if I were to do like cosine of 30 degrees, and then, or if I was to say, cosine of pi over 6, well, that's going to be root 3 over 2. So that's an exact value, root 3 over 2. Versus, like if I do tangent of 5 pi over 4, I know that if I plug this into the calculator, it's going to give me back the answer. It's going to give me back 1. So in that sense, like that's me telling you that you gotta basically be able to work with radians and the exact values for their trigonometric functions. So in that case, be sure that you do look at the 45 90 triangle. So like you have 1, 1, and then you have root 2, but that's going to be pi over 4. That's going to be pi over 4. And then you have the 30-60 triangle, where you have, um, yeah, where you have basically, you have that this is 1, and that's root 3, and that's 2. But this would be pi over 6, and this would be pi over 3. That way it's a lot easier for when you're evaluating these trigonometric function values. Okay, so this will come back basically, when we start looking more at the, really, to be honest, the unit circle. Okay.